Quantum computing solutions ranked by qubits required. Executive summary. Quantum computing applications scale with qubit count, distinguishing between noisy physical qubits and error-corrected logical ones. Small systems, 10 to 100 qubits, support testing, education, and simple chemistry simulations. Mid-range tasks, hundreds to thousands of logical qubits, enable optimization, quantum machine learning, and materials research. Advanced goals, modeling superconductors, industrial catalysts, and breaking cryptography require tens of thousands to millions of physical qubits. Achieving general-purpose quantum computing demands millions of stable qubits and major advances in error correction. Article: Quantum computers use qubits instead of classical bits. The number of qubits a system has largely determines what kinds of problems it can solve. However, it's important to remember that there are two kinds of qubits: physical qubits, the real qubits in the hardware; logical qubits, stable error-corrected qubits built from many physical qubits. Because today's qubits are noisy and prone to errors, most serious applications need thousands or even millions of physical qubits to simulate just hundreds of logical qubits. Below is a ranked list of quantum computing use cases, ordered from those needing the fewest qubits to those requiring the most. 1. Hardware testing and basic demos. Qubits needed, approximately 10 to 50. Used for testing, calibrating, and verifying hardware or algorithms. These are small, short-depth circuits, mainly for research and education. 2. Small molecules, chemistry simulations. Qubits needed, approximately 20 to 100 logical, used with the variational quantum eigensolver, VQE, algorithm to model molecules like hydrogen, H2, or lithium hydride, LiH. Helps chemists understand chemical bonding and energy levels at a basic scale. 3. Optimization problems, QAOA. Qubits needed, approximately 50 to 200. The Quantum Approximate Optimization Algorithm, QAOA, is used to find the best solution among many options, such as for scheduling or portfolio selection. Results are still experimental. Scaling up is difficult due to noise and depth limits. 4. Quantum machine learning, QML. Qubits needed, approximately 100 to 500. Applies quantum circuits to machine learning tasks like classification or pattern recognition. Promising for data-rich fields, but loading data and reducing circuit depth are major challenges. 5. Medium-scale chemistry and materials research. Qubits needed, approximately 1,000 to 10,000 logical. Quantum algorithms like phase estimation are used to simulate larger molecules or complex materials. Could eventually support drug design or advanced materials engineering. 6. Strongly correlated systems, physics models. Qubits needed, approximately 10,000 to 100,000 logical. Models like the Hubbard model describe materials with complex electronic behavior, such as superconductors. These problems are too hard for classical computers, but a natural fit for quantum ones. 7. Industrial catalysts and reactions, e.g. FEMOCO. Qubits needed, tens of thousands to hundreds of thousands logical. Targets important chemistry like nitrogen fixation or battery materials. Recent research has cut the expected qubit requirements by improving algorithms and error correction. 8. Cryptographic key search, Grover's algorithm. Qubits needed, a few thousand logical. Theoretically halves the search time for brute force attacks, e.g. against AES encryption. However, it requires astronomically many iterations, so it's not practical yet. 9. Elliptic curve cryptography, ECC cracking. Qubits needed, approximately 2,000 to 3,000 logical. Shor's algorithm can break ECC-based systems like Bitcoin's SECP-256K1 curve. Even so, billions of physical qubits would be needed with today's error rates. 10 RSA, 2048 cryptography, Shor's algorithm. Qubits needed, approximately 20 million physical, classic estimate. A quantum computer could factor large numbers and break RSA encryption. Some newer studies claim this might be possible with fewer than 1 million physical qubits, but that's still far from current hardware limits. 11. Large-scale, general-purpose quantum computers. Qubits needed. Greater than or equal to 10,000 to 100,000 logical, approximately 10 million plus physical. Would be capable of running multiple scientific and engineering applications reliably. New error-correcting codes, like LDPC and surface code variations, aim to reduce the total qubit overhead by large factors. Quantum computer use cases ranked by qubit needs. This table lists major quantum computing use cases ranked by the approximate number of qubits required. Values are rough estimates that vary based on whether qubits are logical error-corrected or physical actual hardware. Category: approximately logical qubits. Main applications: basic demos, 10 to 50, testing, calibration. Small chemistry, 20 to 100, H2, LIH molecules, optimization, QA/OA, 50 to 200. Scheduling, logistics, quantum ML, 100 to 500. Pattern recognition, medium chemistry, 1,000 to 10,000. Drug design, materials. Physics models, 10,000 to 100,000. Superconductors, catalysts, FE-MOCO, 10,000 to 100,000 plus. Industrial reactions, AES search, few thousand. Cryptography, ECC cracking, 2 to 3,000. Blockchain security, RSA factoring, approximately 20 million physical. Encryption breaking, general FTQC, 10,000 to 100,000 logical. Broad scientific use, key takeaways. We're in the hundreds of qubits era. Current machines are good for demos and small chemistry problems. True quantum advantage likely needs thousands of logical qubits, which means millions of physical qubits with current error rates. Cryptography breaking and large-scale materials design remain long-term goals, but every hardware and algorithmic improvement narrows the gap.